Assalamu alaikum. Good morning. Today I am going to explain you the concepts of differentiation, which is covered in P1 chapter 8. Now, differentiation is a branch of mathematics which involves with changing the rate of a functions. A lot of natural systems is modeled using the either differential equation or as a difference equation. So, in order to solve these problems and find solutions, we need the techniques of differentiation, basically in general the ideas of calculus. Differentiation is one of such branch of calculus. So, in today's lesson I am going to explain you the concepts of differentiation covered in our P1 book. Before I move on, let me just quickly go over the learning objectives that probably we will be able to cover in today's lessons. To find the derivative of a function, simple functions, using the derivatives or the differentiation techniques to solve the problems involving gradients, tangents and normals, finding the second order second derivatives of a function or simple function in generally. But before I proceed, all the functions that will be discussed in today's lesson will be functions with single variable functions generally defined on x only. Some of the terminologies that may come across during this topic is first derivatives. Well, the derivative means the rate at which a function is changing with respect to the variable. So, if a function is defined in terms of x, that will be the rate at which y changes with respect to x. As we change x, how quick y is changing. This derivative is generally referred as the first derivative of a function. Well, there can be first derivative, second derivative, third derivative. When you differentiate once, we call it the first derivative. When you differentiate twice, we call the second derivative. When you differentiate three times, we call the third derivative, like that. The gradient is the instantaneous rate at which the function is changing. So, at a particular time or at a particular x value, what rate is the function changing? That is what we mean by the gradient. That gives you a numerical value, a number. Tangent, a tangent is a straight line that we draw, we just touch the curve at the given point. The normal is a straight line that is perpendicular to the tangent at the point of the tangency, which is the point on the curve. Now, let me go on to the example. First, one examples of the ideas of the derivative. Find the derivative of the function f of x is equals to x squared. Now, the curve f of x is equals to x squared. If you draw the sketch of that, it would be probably something like this. Just touch the point 0, 0, a parabola. So, I am interested to find the rate at which this particular function is changing at the point 1, 1, which is basically the gradient of the tangent that we draw at the point 1, 1. So, in order to study this, what we can do is we can take first an arbitrary point on the curve. Let us say, for example, the coordinate is x, f of x. My equation is y is equals to x squared. Well, if you joined these 2 points on this curve, then we call this is a chord or sometimes a secant line. In order to find the gradient of the curve at the point 1, 1, what we can do is we can find the gradient of this chord, which is using our simple formula m is equals to y2 minus y1 over x2 minus x1 gives you f of x minus 1 divided by x minus 1. Having said my function in this case is f of x is equals to x squared, if I substitute it here, I get x squared minus 1 divided by x minus 1, which after a simple algebraic simplification, the numerator becomes x plus 1 and x minus 1, which is factorization of difference of squares divided by x minus 1. Cancelled out the common factors, that simply gives you x plus 1. But what I am trying to find is the derivative of the function or the rate at which the function is changing at the point 1 comma 1. Now, as x gets closer to 1, if I bring this point closer to 1 comma 1, what would happen is the x value will approach to 1. So, as x approaches to 1, the derivative m becomes 1 plus 1, which is equals to 2. So, that gives you the gradient of the tangent to the curve at the point 1 comma 1. But this is a very tedious method if we try to find the gradient of any point on the curve every time doing this method to find the gradient. So, we need a better techniques or better methods to find the gradient. Now, so in differentiation, what we will be studying is in general how do we find the gradient of a curve, or how do we find the rate at which the curve is changing. So, I am going to now show you how to find the derivative of the curve f of x is equals to x squared in general, not just at a point like 1 comma 1. So, let me choose an arbitrary point on the curve with coordinate x comma x squared. The y coordinate is x squared in general. So, the x coordinate is x, the y value is x squared. I am going to take another arbitrary point on the curve that is at a distance h units from x. So, the x coordinate would be x plus h. Hence, the y coordinate would be x plus h whole thing squared. So, I am going to use the same similar techniques that I used in the previous example. So, my gradient m, that is equals to x plus h whole thing squared minus x squared divided by x plus h minus x in general. Now, after algebraic expansion, the numerator becomes x squared plus 2xh plus h squared minus x squared divided by x plus h minus x. There are some simplifications that we can do here. X squared and minus x squared cancelled out, x and minus x cancelled out. This gives you 2xh plus h squared divided by h. Simple factorization on the numerator gives you 2x plus h times h divided by h, which gives you the expression 2x plus h. Now, what we are interested is what would happen if I bring this particular point sufficiently close to this point x comma x squared. If I bring this particular point close here, what would happen is this h becomes very small, and hence h will be close to 0. So, we say as h tends to 0 or h gets closer to 0, the gradient will be equals to 2x plus 0, that gives you 2x, which gives you the derivative of this particular function at the point, at any arbitrary point. We write this in general, the derivative of a function f of x is equals to the limit as h tends to 0 f of x plus h minus f of x divided by h. We get that h after cancelling those two x values. So, that is what we mean by the derivative of the function from first principle. Well, having said that, now that's a function. How do we find the derivative of the function f of x equals to x squared? So, in general, in order to define the derivative of the function, simple functions, we will first have a look at the derivative of the power functions. Okay. Here I have selected some common or some simple power functions. When the function is equals to just 1, is using the laws of indices, that is same as x to the power 0. Anything to the power 0 is equals to 1. So, the derivative of that function is 0 because f of x is equals to 1 is a horizontal straight line. The y value does not change at all. So, the numerator of this particular expression will be 0. So, the derivative of that function gives you 0. F of x equals to x, the derivative is 1, x squared as I have shown you is 2x, x cube, when you differentiate we get 3x squared. So, in general what is it going to be? When you have function x to the power n, a power function, it is n times x to the power n minus 1. Using a similar approach and using the ideas of binomial expansion, we can show that. Similarly, if you have a negative power, say for example x to the power minus 1, it is minus x to the power minus 2. So, basically what this shows is when you differentiate power functions, what we do is we multiply the power by the coefficient and then subtract 1 from the power. So, the order of proceedings is first multiply the power by the coefficient, second step is subtract 1 from the power. That is the order that we follow. So, that gives you the simple power functions derivative. Now, in order to find the derivative of the general functions, we are going to use this idea to find the derivative of complex functions, that is functions that are generated from other functions. Now, on this table what I have listed is some of the common functions and then some of the functions that are derived from other functions and their derivatives. If you have a constant function y is equals to c, the derivative is 0. As I said again, constant function is a straight line, horizontal straight line, there is no change in y values. So, the derivative is 0. An example is y is equals to 3, the derivative gives you 0. When we have a constant times a function, that is simply the derivative of the function times the constant. So, the derivative of constant times the function is constant times the derivative. An example is y is equals to 3x squared. Here x squared is a power functions or the examples that I have been using. So, I multiplied that x squared by 3, 3 is a constant number. So, the derivative of that is 3 times the derivative of x squared. The derivative of x squared is 2x. So, that gives you 3 times x squared, 3 times 2x giving you 6x. Then we have sum of functions. Well, the sum of the derivative of the sum of the function is same as the sum of the derivatives of the function. So, f of x plus g of x, the derivative is the derivative of the f plus the derivative of the function g. So, for example, y is equals to 3x squared plus 4x. The derivative is the derivative of 3x squared, as you see here, which is 6x, plus the derivative of 4x, which is 4. Similarly, the derivative of the difference of function is same as the difference of the derivatives of the function. So, if I simply change that plus to a minus, that becomes the difference of two functions, which gives you the derivative 6x minus 4. So, these are the fundamental rules that we will be using in P1, but these are not the only differentiation rules, only few. Let us do few examples. Find dy by dx when y equals to 3x squared minus 6x to the power minus 1 plus 2x to the power half plus 3. In these examples, you see constant times functions, difference of functions, sum of functions, and also constant functions. So, basically this particular examples involves all the rules that we have seen in the previous slide. If you differentiate this one, what you get is 6x plus 6x to the power minus 2. Why we get a plus? Because minus 6 multiplied by minus 1 gives you plus 6. X to the power minus 1 gives you minus 2. Similarly, for the third term, 2 times the power minus half gives you, that must be a minus x to the power the power is plus half. So, 2 times plus half give you plus 1. So, plus x and then subtract 1 from the power half minus 1 gives you minus half. And the fourth term, which is a plus 3, that is a constant term when you differentiate, which is 0. Second example is little complicated. 3x squared minus 6 divided by x. always make sure before you start differentiation, all the terms in the expression is written in the form ax to the power n. That you can do using the laws of indices that you have studied in chapter 1, section 1.1. So, if you do that, first thing is we can split this into two fractions. When the denominator is a single term and the numerator can be many, you can always split that fractions into sum or the difference of terms. If you do that in this case, you get 3x squared divided by x minus 6 over x. Then use the laws of indices to simplify this expression. Gives you 3x minus 6x to the power minus 1. Be careful, we haven't differentiated that yet. It's just using the algebra, we have written every term in the form ax to the power n. Then you can apply the differentiation techniques that we have discussed. 3x when you differentiate, it's 3, minus 6x to the power minus 1 when we differentiate, we get plus 6x to the power minus 2. One of the examples, one of the applications of differentiation is finding the gradient of the tangent and the gradient of the normal, or finding the equation of the tangent or finding the equation of the normal at a given point. Now, this example says find the gradient of the curve y is equals to x cube minus 3x plus 2 at the point minus 1, 4. So, in order to find the gradient, the first thing we need to do is differentiate, find the derivative function. As I showed in the first example, we can find the derivative and then substitute an x value of a point on the curve to get the gradient of that point. So, derivative gives you a function that you can use to find the gradient of the tangent to the curve at any given point. So, if we find the derivative of this function using the rules, you get 3x squared minus 3, and then we substitute the x coordinate of the point minus 1, 4, which is minus 1. We get 3 times minus 1 squared minus 3, which simplifies to 0. So, the gradient of this curve y is equals to x cube minus 3x plus 2 at minus 1, 4 is 0. To find the equation of the normal, equation of the tangent over normal, well, there are a few steps that we can follow. First is we can find the derivative of the function. Second step is we can find the gradient of the tangent at that point in both cases. Now, if it is a normal, we also need to find the gradient of the normal. For that, we can use the properties of perpendicular lines. And then we can use the equation of a straight line that we covered in chapter 5, section 5.2 to get the equation of the tangent or to get the equation of the normal. Now, this is a exam style questions which shows the point 3, 16 as you see on the right side diagram lies on the curve. Find the gradient of the tangent to the curve at P. The equation of the curve is x squared plus 3x minus 2. So, we want to find the gradient of the tangent to the curve at P. In order to do that, our first step is differentiate. So, I am going to demonstrate that on the board. My curve is y is equals to x squared plus 3x minus 2. So, part A, find the gradient of the tangent to the curve at P. To do that, first we differentiate. So, dy over dx, very important to write this symbol, 2x plus 3, that simple expression is our derivative. So, to find the gradient of the tangent to the curve at the point 3, 16, we substitute the x coordinate which is 3. So, at the point 3, 16, we get dy over dx is equals to 2 times 3 plus 3, that gives you 9. Second part is the point Q with x coordinate 3 plus h, somewhere on the curve we have a point with x coordinate 3 plus h, that means h units to the right of 3 also lies on the curve. Find in terms of h the gradient of the line PQ. Write your answer in the simplest form. So, first we also need to find the point Q with coordinate 3 plus h. We may also need to find the y coordinate, because they asked you to find the gradient of PQ. So, at x is equals to 3 plus h, the y coordinate would be 3 plus h whole thing squared plus 3 times 3 plus h minus 2. Well, after some simplification, this is 3 squared 9 plus 9 16 6h. So, we get 9h, that is 6h plus 3h plus h squared. That is the y coordinate of the point at x is equals to 3 plus h. So, we got a point whose x coordinate is 3 plus h, y coordinate is 16 plus 9h plus h squared. So, the gradient is m is equals to y2 minus y1 over x2 minus x1, 16 plus 9h plus h squared minus p whose coordinate is 16 divided by 3 plus h minus the x coordinate is 3, which simplifies to 16, 16 cancelled, 3 and 3 cancelled, which simplifies to 9h plus h squared divided by h. Well, this can be further simplified as we can factor out h from the numerator and cancel with the denominator h, giving you 9 plus h. That is the gradient of the line PQ. Part C says, explain briefly the relationship between answer to B and answer to A. Now, what would happen if h tends to be 0? If h tends to be 0, this particular point 3 plus h comma 16 plus 9h plus h squared will be sufficiently close to P. So, as h tends to 0, the gradient m will be equals to 9. So, that gives you the gradient of the tangent to the curve at x is equals to 3 or at P. So, that is how we answer this question. Another example. A curve has equation y is equals to 4x squared plus 9 divided by 2 root x. Find x coordinate of the point on the curve at which dy by dx is equals to 0. Now, this is an application question where the gradient is given, asking you to find the x coordinate. So, this involves the differentiation techniques as well as algebra. Y is equals to 4x squared plus 9 divided by 2 root x. Well, it says x is a positive number. So, if we get a positive and a negative value, then we choose in this case the positive value. Question says dy by dx is equals to 0, which means after the derivative, when we substitute an x coordinate, our answer is equals to 0. Question is, what is that value that we are substituting? So, in order to do that, first we are going to find the derivative. Well, as I said, we need to write every term in the form ax to the power n before we start differentiation. Well, remember, using laws of indices in chapter 1, root x is same as x to the power half. So, this particular expression can be written as 4x squared divided by 2x to the power half plus 9 divided by 2x to the power half, which after simplification becomes 2x to the power 3 by 2 plus 9 over 2x to the power minus half. The variable x is in the denominator, so we take it to numerator, which is same as using the laws of indices x to the power 0. So, 0 minus half gives you minus half. Now we are ready to differentiate because every term is now written as ax to the power something. Derivative dy over dx. Using the rules, we multiply the coefficient by the power. 2 times 3 by 2 gives you 3. X to the power 3 by 2 minus 1 gives you half. 9 over 2 times minus half give you minus 9 over 4. X to the power minus half minus 1 give you minus 3 by 2. That gives you the derivative of this particular function. Now the question is, when we substitute an x value, our answer is 0. So what that x value is? So to do that, we equate this derivative 3x to the power half minus 9 by 4x to the power minus 3 by 2 equals to 0. And then we solve this equation. Now you see x appears in both, so we can use factorization. In factorization, it is always recommended to take the least power to out. So we get x to the power minus 3 by 2. If you do that, we get 3x to the power 2 minus 9 over 4. Factorization gives you that equals to 0. Using the zero product property, which states the product of if any two real number is 0, then one of them must be equals to 0, tells us x to the power minus 3 over 2 should be 0, or 3x squared minus 9 over 4 should be equals to 0. One of them has to be 0. But x to the power minus 3 by 2 is never 0 because this is reciprocal power. So this is never 0. Absurd. That won't happen. So the only choice is 3x squared minus 9 by 4 is equals to 0. Solving these equations give you x squared is equals to 9 by 4. Sorry, 3x squared is equals to 9 by 4, or x squared is equals to 9 by 4 divided by 3 gives you 3 by 4. So x is equals to square root of 3 by 4. Well, generally we do have a plus or minus, but in this case not necessarily, because the question says x must be a positive number. So x is equals to square root of 3 divided by 2. That is our answer for this one. So when we substitute x is equals to root 3 over 2 to this derivative, we will get 0. That's what the question is asking us to find out. So these are two examples which I have selected from the IAL past papers, which involves the differentiation techniques. There are more questions that you can use, practice at home. All are from IAL 2018 new syllabus, January 2009, question number 6, question number 12A, which you can practice at home. Thank you very much. Before I conclude, just take your personal responsibility and follow the instructions of the Health Protection Agency. Thank you very much. Good luck.